10.4, here we go, area as a limit. So we've done 10.1 and 10.2, and we've looked at how to calculate the area under a curve by taking the antiderivative and doing the definite integral on a boundary, on a interval. I can't even speak. But we're going to look at some specific cases in which the antiderivative of a function is actually really difficult or impossible to find. And so we have to come up with a different method, a numerical method, to estimate the area under F. So if you have time to pause and just look at this motivating example, it's lessons 1 and 2 from the University of Waterloo. It'll take you about 20 minutes if you have time. It has to do with velocity and area under a curve, and it's really great. We are going to leap into their intro to the area problem. I am going to show you this little piece right here to start before I get into dividing our area under the curve with geometric strips. Okay, so I'm going to link to these. If you don't have time to do the motivating example, that's okay. But I do really like how they intro the area problem. So we're going to start with their little video.
We will see that many problems can be solved by finding the areas of regions in the plane. In particular, the total distance traveled by a car can be calculated by finding the area beneath the curve y equals v of t over some time interval a, b. So we have a limited bank of formulas for computing areas of two-dimensional objects, things like rectangles, triangles, circles, but we don't really have a guarantee that our region in question will be able to be subdivided into recognizable shapes. Maybe it has curved sides that we don't recognize. So how are we going to do this in general? Well, here's our method. So we're going to approximate a region by rectangles, and we're going to take the limit of the total area of these rectangles as we increase the number of rectangles we're allowed to use in our approximation. So we'll illustrate this with an example. Let's find the area under the graph f of x equals x squared plus 1, and above the x-axis on the interval 0, 1. So that was a bit of a mouthful, and all of those pieces of information are important. So it tells us that our region is bounded by the curve x squared plus 1, the x-axis, and the two vertical lines x equals 0 and x equals 1. So you can have a look at what that area is, and observe that the area we're looking at is not a regular shape. It's not a shape that we recognize. So to estimate the area of our irregular region, we're going to use several rectangles. Let's begin with, say, 5 rectangles. So first, we're going to divide our interval 0, 1 into 5 equal subintervals, just to start sounding familiar now. Since the interval 0, 1 has length 1, each subinterval is going to have length 1 over 5. So the divisions of our interval will occur at the following points. X equals 0 on the left-hand side. Then if we move over 1/5, we get to x equals 1/5, and so on. We get 2/5, 3/5, 4/5, and then 1 at the right endpoint. We're going to draw vertical lines at those 6 points from the x-axis all the way up to where we hit our function, and that's going to divide our region into 5 vertical strips. Now we're going to approximate each of these 5 irregular regions by a rectangle, where we can actually compute the area of the rectangle. So we're going to actually provide you with 3 different approximation methods here. The first one we're going to try is going to be called the left rectangular approximation, where we're going to be using 5 rectangles. L stands for left, and 5 is the 5 rectangles. So the width of each rectangle will be the width of the vertical strips, while they're all equal to 1/5 the length of the subintervals. The height of each rectangle is going to be the same as the left edge of the given strip. We can see that in the picture. So in other words, the heights of the rectangles are going to be the function values at the 5 left endpoints of our 5 subintervals. F of 0, f of 1/5, all the way down to f of 4 over 5. So of course we're leaving out f of 1 here, because 1 isn't the left endpoint of any of the intervals. So we can see all of these 5 rectangles drawn in our picture. So now to calculate this quantity L5, our approximation, we're going to add up the areas of all 5 rectangles. So we take the base times the height for each rectangle, and we add them as you see here. So the area of the first rectangle is the base 1/5 times the height, which is f of 0, and so on. So as we plug in our values, remember here that f of x is x squared plus 1. We plug in all of our values into our function, and we get 1.24 as an answer. So this tells us that our first approximation using 5 rectangles is 1.24 units. So we can see some things right away. If you look at the picture, it looks like our estimation is actually low. You can see that the area covered by our rectangles is actually smaller than the area covered by the whole region. So we can say now that 1.24 might be a pretty good lower bound for the area of our region. Now the second approximation method we're going to use is called the right rectangular approximation, again using 5 rectangles. Here the R stands for right, and again the 5 is telling us how many rectangles. So this process is similar, except for here, to find the height of each rectangle, we're going to take the right side of the vertical strip for the height. In other words, the heights of the rectangles will be given by the function values at the right endpoints. So those right endpoints are 1/5, 2/5, all the way down to 1. Now note that 0 is now excluded because it's not the right endpoint of any interval. Again, if we add up the areas of those 5 rectangles, as you see here, we get 1.44. We get more information from this. From the picture, it looks like these rectangles are now overshooting the area. The total area they covered is bigger than the area of our region. So we get a nice upper bound for our region of 1.44. So we're doing pretty well. We know at least that our region is trapped between 1.24 and 1.44. So the last method we're going to look at for this is called the midpoint rectangular approximation, again using 5 rectangles. So now as you see in the picture, we're going to add an extra vertical line here at each midpoint of the subintervals. So at 1/10, 3/10, 5/10, 7/10, and 9/10. Now we're going to let the height of the rectangles be determined by the function values at each of those midpoints of the subintervals. So here, again, M is telling us we're using midpoints, the 5 is telling us we're using 5 rectangles, and we're going to add up the areas of those rectangles. And here we see we get a value of 1.33. So that guy sits nicely in between 1.24 and 1.44, our left and right approximations respectively. If you look at the picture, you may be able to convince yourself that the midpoint rectangular approximation is the best approximation of the 3. Now we need to ask the following questions. First, how good are the approximations L5, R5, and M5? We can get some idea from the picture. Second, how much better would the approximations be if we used 10, 20, or even 50 rectangles instead of 5? In theory, we can calculate the left, right, and midpoint approximations for any number of rectangles. In practice, once the number of rectangles gets large, we'll probably need the help of technology to do the arithmetic. So fix some number, say n. If we divide the interval 0, 1 into now n equal subintervals, we can repeat the same process. Well, our interval has length 1, and we have n equal subintervals, so each one is going to have length 1 over n. If we draw our vertical lines again at those divisions, we're going to divide our region into n vertical strips. And again, we approximate each strip by a rectangle. Well, we can use our left approximation, or our right, or a midpoint. So here, if you look at the pictures, we're letting the computer do some work for us, and we can see exactly what those approximations look like. Here we see n equals 10, so 10 subintervals of length 1 over 10. Observe that the left, right, and midpoint approximations are each displayed. Next, we see the left, right, and midpoint approximations for n equals 20, each consisting of 20 subintervals of length 1 over 20. Now, if you look at the picture, it should be pretty clear that as n gets larger here, our approximation's getting better. What do we mean by that? Well, if you see the area covered by the rectangles versus the area covered by the graph, the difference between them is getting smaller and smaller as n gets larger. So this is some good evidence that, well, if we want to get an exact value for the area, we want to look at these types of approximations, but let n get bigger and bigger and go off to infinity. So here's a little table of values where we let the computer generate a bunch of other approximations for ln, rn, and mn for larger and larger n. So here it looks like our left-hand approximation starts at 1.24, which we've seen, and goes to approximately 1.33. Similarly, our right approximation started at 1.44, and it looks like it's approaching, again, something around 1.33. If we look at our midpoint approximation, it starts at 1.33, and if we look down at n equals 1,000, it looks like it's converging to 1.3 repeated. So one thing to note, just from this small amount of data, is that all of our approximations seem to be approaching very similar numbers. So one reason for this, if we think about it, may be because as n goes to infinity, the length of the subintervals is going to 0. So we're really adding up very good approximations for the area under the curve for really small subintervals.
All right. So that brings us back here. And that hopefully makes these diagrams have a little bit more, make a little more sense. If I can get it in the right spot. So if we can divide the area under the curve into geometric strips using vertical rectangles, then we can use the areas of those rectangles to approximate the area of the region. So the first diagram is showing the right side, as she showed. So the right boundary is the vertical height on these. And then the middle one is the midpoint diagram that she showed. And this one just has 5 vertical strips. And then the last diagram has the left as the boundary. This was her 0, the very first one that she showed at 0. And so these are just showing the boundaries going from x0 to x5. So this is just showing whatever that x value is, and we're dividing this into 5 strips, okay, where n is 5 in this diagram. So it's important to notice that the width is the change in x. Okay, the width is represented by that change in x, which would be represented by taking your left boundary, in this case x5, minus the right boundary, and dividing by however many strips you have. So we could write a generic b minus a all on n to get the width of each of our rectangles. And then the height of each rectangle comes from calculating whatever x value is going into your function, okay? And so down here we have our formula. So the area is going to equal to the sum of the rectangles. So this represents rectangle number 1. And then the next one is rectangle number 2. And so forth, 3, 4, and 5. And then you add those all up and you get the approximate area under the curve. Now, I know we've learned how to do this with x squared plus 1, but we're really talking about what happens if the curve is something weird, and which, if you saw the motivating example, you would have seen. So what happens, if the curve is doing something weird and is not a nice function to work with? We're working with nice functions today just to make the math a little easier. Okay, so I'm going to pause the video here and come back and explain this little symbol here and move forward with some examples with you.